So, worksheets 2 through 5 will be due on the 6th. Exam number 3 will be due also on the 6th. And homework number 3 will also be due on the 6th. That's next week, Thursday. Exam number 3 is going to be 60 questions. Like the previous exams, you get 1 sheet of notes. The last exam will be early December. And it will be immediately followed by us doing the presentations. If you haven't signed in, please sign in on the sheet. So let's get started on Chapter 7. So we talked about volcanoes, which is one way that mountains can be formed. Let's talk about the other ways that they can be formed and just the general methods that the crust gets deformed and mountains get created. We'll talk about the 3 types of differential stress and the tectonic setting that are most commonly associated with each. We'll talk about the difference between stress and strain, and brittle and ductile deformation. We'll describe 5 different types of folds. We'll list and describe 5 types of folds. We'll describe the relative motion of rock bodies, located on opposite sides of normal, reverse, and thrust faults, as well as both types of strike-slip fault. Both types of strike-slip fault. We'll locate and name its major mountain belts on a world map. We'll talk about how an Andean type mountain belt is generated and its cross section. We'll go over the developments of an alpine type mountain belt, such as the Appalachians. We'll explain the principle of isostasy and how it contributes to the elevated topography of mountain belts. So the crust deforms. It doesn't always stay the same shape. Deformation is a general term that refers to all changes in the shape or position of a rock body in response to stress. It's just changes in the shape of something in response to stress. Stress being force applied. So stress is like force. So rock or geologic structures are the features that result from forces generated by the interactions of tectonic plates. There are various structures that can form. This includes things like folds, where the crust bends, faults, where the crust slides along a break, and joints, where the crust doesn't slide along a break. So the difference between a fault and a joint is just that a fault is moved and a joint is not. So here's an example of some deformed sedimentary strata. We have some folding here. So these layers were once all flat, and then they got squished and bent. And so this would be a syncline because it's a trowel shape. The other way around is an anticline. Here is a fault, where you can see the layers have moved relative to each other, but the whole thing, this is a fold. So there's 2 ways that something can react to stress, 2 ways that it can deform: brittle and ductile. Ductile is when it bends or squishes or distorts in some way without breaking. Brittle deformation is when it breaks. So generally, softer things deform more ductilely, harder things deform more brittly.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to distinguish between brittle and ductile deformation and explain where in the crust each style of deformation is most likely to be found. We've discussed brittle versus ductile deformation before when we talked about the difference in the way rocks behave at shallow depths in the crust versus greater depths in the crust. And basically the take-home message was, at shallow depths in the crust, rocks are more likely to break, producing rocks like fault breccia, whereas at greater depths, when the rocks are warmer and under more pressure, they're likely to deform in a ductile fashion, producing rocks like myelinite. So let's take a look at this figure from your textbook. It shows how rocks respond to differential stress depending on whether they are shallow in the crust or whether they are deep in the crust. Let's first take a look at compressional stresses. Compressional stresses cause rocks to break by reverse faulting, and rock masses get shoved on top of their neighbors if you're at shallow depths in the crust. At greater depths in the crust, you end up getting folding. If your dominant stress is actually tension, then the shallow crust will deform by faulting again, but this time it's normal faulting. So this time the blocks of rock are sliding down the face of the neighboring blocks of rock. At deeper levels in the crust, the rocks simply stretch out and elongate. Lastly, there's the possibility of shear. Shear will produce transform faults in the shallow crust, and the rocks will end up producing shear zones in the deeper crust. Here's some examples of brittle deformation, joints and faults. Both joints and faults are fractures in the rock. There's the trace of both of those fractures. The difference between them is simply that there's no offset along a joint, whereas a fault does have an offset, and you can spot that offset if you have a good marker bed like that one there. Here's an example of ductile deformation, not a geological example, but it still illustrates the concept. A quarter that's been smushed by a train going over it. You can see the quarter's been flattened and it's been elongated in one direction. So that's typical of ductile deformation. Let's test you on the concept. Take a look at this. This is a deformed trilobite fossil. You tell me, is this brittle or ductile deformation? Hopefully you said this is ductile deformation. If the trilobite were snapped in half, it'd be an example of brittle deformation, but here the trilobite has flowed into a new shape, so that is an example of ductile flow. Thanks very much for your attention. This has been another Smart Figure.
So yeah, those machines that squash a penny out to make a new picture, those are all ductile deformation. So, what causes rocks to deform? Well, there is stress. Stress is the force that deforms rocks. So whenever anything has a force applied to it, when you talk about a material with a force applied to it, you can talk about stress and strain. Stress is a measure of how much force is being applied to it. So like my weight is stressing my bones, or the stress, you could have stress from two tectonic plates grinding against each other, the force. And strain is how much the object deforms or changes shape because of that force. So there are three main types of stress. There is compressional stress, tensional stress, and shear stress. And most materials have different strengths against each type of stress. So compressional stress will squeeze a rock and shorten the rock body. Tensional stress pulls apart a rock unit and lengthens it. And shear stress is this sort of side-to-side motion that produces a motion similar to slippage that occurs between individual playing cards when the top of a stack is moved relative to the bottom. Where instead of being a rectangle, it ends up being a parallelogram. That's shear. And in general, most materials are stronger in compressional or tensional than against shear. Things tend to be weaker to shear stress. So here are some examples of different types of force that you can experience on the ground. There's first confining pressure. Confining pressure is when you have equal pressure from all directions. So there's no net stress there, you're just squeezing everything. Compressional stress is shortening along one direction. Tensional stress is stretching along one direction. And shear stress, you have sort of pushing one way on one side and the other way on the other side, and that shears it. Now, strain is a change in shape caused by stress. So while and strain can be temporary or permanent. You can have a temporary strain where it will bounce back after the stress is released, or you can have actual permanent change. So strain is the change in shape of a rock caused by differential stress, and strain bodies will lose their original configuration during the process of deformation. So if they deform permanently, they're not going to change back. So here's shear and the resulting deformation. So if you have tiny movements between the playing cards next to each other and move back, rock is somewhat elastic, so it can actually bounce back after stress has been applied, but it's not hugely elastic. So deformation can happen in a few different ways. You can have elastic deformation, which is things change configuration because they're deformed, but they can bounce back. Rock will return to nearly its original size and shape when the stress is removed. This is what springs do. But there's some limit. There's an elastic limit for any material, where after which the deformation will be permanent. So that's the strength. Once the elastic limit or strength of the rock is suppressed, it will either bend, undergoing ductile deformation, or break, undergoing brittle deformation. And whether it bends or breaks depends on properties of the rock, but also things like confining pressure can have an effect on that. So things that affect how rocks will deform. Temperature. The warmer rocks are, the hotter they are, the more likely they are to bend instead of break. Confining pressure. So ductile deformation is more common when things are warm, and brittle deformation is more common when things are cold. This is something you can just observe in your day-to-day life. Cold things are more likely to snap and break. Warmer things are more likely to bend, generally. Confining pressure. If you squeeze a rock together, it actually makes it harder for it to deform by breaking, and it's much more likely to undergo ductile deformation. It makes it stronger against breaking, and thus more likely to deform ductily. And then the types of rock. So crystalline igneous rocks generally experience brittle deformation. So if your igneous rocks got lots of crystals in them, those are much more likely to crack or break. Whereas sedimentary and metamorphic rocks with zones of weakness are more likely to have ductile deformation, because those weaker areas are where things can move around and bend. And time. Faster forces are more likely to cause brittle deformation. Forces over a longer period of time, more likely to cause ductile deformation. So whack it with a hammer, it breaks. Slowly push on it, it's more likely to bend. Now, the deformation that's caused by different types of stress, you tend to have brittle deformation at shallow depths and ductile deformation at deeper depths. And then the three types of stress each create different types of deformation. So let's start with shallow depths. If you're compressing material together, squeezing things together, you get reverse faulting, where the head wall slides up above the foot wall. And that shortens the length of the crust. It shortens the length of the ground. You slide the head wall up over the foot wall. I put some arrows here to show you how things are moving. If you have tension, which causes lengthening and things to stretch out, you get normal faulting. The foot wall slides down the head wall, lengthening out the ground. It's like you're sliding things apart, making more room. And for shear, you get strike slip faulting, where one side goes to the left, the other side goes to the right. Or vice versa. At depth, you tend to get ductile deformation. If you're compressing things, well, to make things shorter, they end up folding up. Like if you have a piece of paper and you try and squish it, it bends. You get folded. If you're stretching it, if you're pulling it apart with tension, it stretches. It lengthens it out, like pulling on taffy. And then shear forces sort of bend it sideways, as shown here. It's a little hard. It's always a little hard to describe what shear forces do. So let's talk about folds. These are changes that are generally caused by compressive forces at depth. And they're structures formed by ductile deformation. So often you get rocks bent into a series of wave-like undulations called folds. Most folds are the result of compressional stresses from like when continents collide or when continental plates are being driven into each other that result in a shortening and thickening of the crust. So to make the crust shorter, it has to get thicker because the material isn't vanishing into the ether. It has to go somewhere. So the most common types of folds are, or the simplest sort of folds, are anticlines and synclines. Anticlines are sort of arched folds, like this. They're sort of cup, the opening of them is pointed downwards. The oldest strata will be in the center when they erode away. And synclines are the opposite. They're downfolded or troughs of log layers. They're sort of cupped upwards like this. So the youngest strata will be in the center. So you have anticlines, which are arches, and synclines, which are troughs. This folding occurs when slow compressive forces apply extreme pressures on the rock layers, and the forces that cause folding can be exerted either horizontally or vertically. Mostly we're going to talk about horizontal forces. And in general, folding is something that happens in the early stages of mountain building. Things fold first, and then later you start to get these large faults, where the forces build up too much for brittle transformations have to occur. So depending on the orientation, anticlines or synclines can be described as either symmetrical, the sides are the same, or asymmetrical. The sides of the fold aren't identical. Say one side is steeper than the other. And the most extreme of these are overturned. These are folds that are sort of S-shaped, where one or both limbs is tilted beyond the vertical, and plunging is where the axis of the fold penetrates the ground. So here are, and in an extensively folded area, it's a particular rock layer's resistance to erosion that determines what type of feature is formed. So anticlines don't always form ridges, and synclines don't always form dips, because it depends on how various rocks weather in a road. So here are some common folds. We have an anticline and a syncline. Here we have an asymmetrical fold where it's tilted. And then over here we have an overturned fold where it's in fact above the other. So the limbs of a symmetrical fold tip in opposite directions about the same amount. In an asymmetrical fold, one is steeper than the other. And they dip at different angles. And an overturned fold is an even more extreme case where both limbs of an overturned fold dip in the same direction, but one has been tilted beyond the vertical. So you get a sort of almost S-shaped structure. So here's a short video about folds.
Hi, this is Callan Bentley. Welcome back for a smart figure about folds. So after watching this video, you should be able to describe the several different major styles of folds and some varieties thereof. So let's begin by taking a look at a folded set of sedimentary layers. There's three major kinds of folds that are shown in this image. There's an anticline, which is a fold that goes up in the middle, a syncline, a fold that goes down in the middle, and then a monocline, which is basically a fold with just one limb or one side. So it's basically horizontal, and then it's inclined, and then it's horizontal again. Here's an example of a syncline. So you can see here that the sedimentary layers are bowed downward in the middle. Here's an example of an anticline. You can see the sedimentary layers go up in the middle. And then here's an example of a monocline where you've got horizontal on the left, inclined in the middle, and then it flattens out again over towards the right. Now, here's a look that's partially a three-dimensional view and partially a cross-sectional view of a fold. You have probably deduced that this one is an anticline. But what I want to point out to you here is that the angle of dip of the left limb is much less than the angle of dip on the right limb. In other words, the strata are inclined more steeply on the right and more shallowly on the left. So we actually have a set of terminology that can describe these sorts of variations as well. We say that a fold is symmetrical if its two limbs dip at the same angle in opposite directions. We say that a fold is asymmetrical if its limbs dip in opposite directions, but one is steeper than the other. A fold is said to be overturned if the two limbs dip in the same direction, but at unequal angles. And then there's a third possibility as well, and that's a recumbent fold. So this is an example of a recumbent fold here. Basically, the fold has been tipped over on its side completely. Okay, let's test yourself. What kind of fold is shown here? Hopefully you said an anticline. Good job. All right, let's try another one. What kind of fold is shown here? Hopefully you identified that as a syncline. Very good. Last one. What kind of fold is shown here? This one's a little trickier, but this is an overturned anticline. So you can see that the two limbs are both dipping in the same direction, but they're dipping at different angles. And the plane that divides the fold in two, the axial plane, has been tipped over on its side. Okay, good job. Thank you very much for your attention. This has been another Smart Figure.
So folds are bends along like a line, kind of. But you can also have things that are more like a point, where a point gets pulled up or sinks down. These are domes and basins. So folds are like long, stretched out bends, but you can also just have like one area being pushed up or pulled down. So domes are upwarp circular features where the oldest rocks are in the center. Basins are the opposite. They're downwarp circular features. The youngest rocks are in the center. So these could be something pushes up from below, causes an area to dome up, or something causes an area to sink down. So here, domes, the oldest strata is in the center, the youngest strata is around the edges. It's bulging up. Here we have a basin. The youngest strata is in the center. The oldest strata is around the edges. It's dipping down. And so the dome is sort of an upwelling, a basin is a sinking.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at structural domes and structural basins. And after watching the video, you should be able to use a couple different lines of evidence to determine whether a particular bullseye pattern on a map is a dome or a basin. We've discussed folds previously, and folds are linear. That is, they have an axis around which the sedimentary layers or other rock layers are warped. However, with domes and basins, it's more of a single point. So there's a point that travels up in a succession of rock layers, or there's a point that travels down. The example on the left is a dome. The example on the right is a basin. You'll notice that the dome is arched upwards in the middle, and the basin is arched downwards in the middle. If you put some strike and dip symbols on these diagrams, they would look something like this. Notice that in the dome, all the strike and dip symbols, the little prongs radiate outward. So they look almost like, I don't know, the spikes on a porcupine. Whereas with the basin, the dip lines all point in towards the middle. That's one way that you can tell the two apart, basically whether the beds are dipping towards the middle, as in the basin, or whether they're dipping away from the middle, as in the dome. Another way you can tell the two apart is with the ages of the different rock units. So an example of that can be seen here in South Dakota. This is the Black Hills of South Dakota. Probably the most famous mountain in the Black Hills is Mount Rushmore. Mount Rushmore, you can see, is made of granite, and you can actually see the granite in contact with some schist down at the base here. So that granite intruded into schist, and that's part of this pink unit over here on the geological map. If you drew a cross-section through that geological map, maybe like that, then that cross-section would look something like this image we see down here in the lower left. And you can see that that central area of schist and granite is basically domed upwards, and that the sedimentary layers dip away from it in all directions. So if you were to draw strike and dip symbols on this map, they would look something like that. Notice that they dip outwards in all directions. Here's an example of a structural basin. It's called the Michigan Basin because it's centered on the U.S. state of Michigan. Notice that if we were to draw a cross-section going through like this, the rock layers basically dip towards the center of this structure. So in the cross-sectional view down here, you can see the rock layers dipping in at both edges. And another thing you'll notice there is that means that the oldest strata, all right, the orange and the pink colored layers, are on the outside. So those are Silurian and Ordovician in age. And the very youngest strata, in this case Upper Pennsylvanian in yellow, those are in the middle of the structural dome. So another way to tell a dome from a basin is whether or not it's got old stuff in the middle or young stuff in the middle. If it has the oldest layers in the middle, that means it's a structural dome. If it has the youngest layers in the middle, it's a structural basin. Okay, so here's a test. Here's a bullseye pattern of rock layers that are outcropping, and you need to figure out whether this is a dome or a structural basin. What are you going to look for? Well, probably the first thing you might look for is the presence of strike or dip symbols. So if I gave you some strike or dip symbols that look like that, would you say that this is a dome or a basin? Hopefully you've deduced that that's a dome because the rock layers dip outwards in all directions from the center, and that's the outcrop pattern that we see with the dome. On the other hand, perhaps we don't have those strike and dip symbols, and instead we just have age relationships. And you find out that the oldest rock layers are on the edge and the youngest rock layers are in the middle. Now, would you say, is that a dome or a basin? Hopefully this time you changed your answer and said that this is a basin, because with basins, the youngest rock layers are in the middle and the oldest ones are towards the edges. Nice work, and thanks for your attention. This has been another Smart Figure.
That was domes and basins. So we've got synclines, which are troughs, anticlines, which are arches, domes, which bulge up at a single point, basins which sink down at a single point. And lastly, we have monoclines, which are sort of like a stair step. These are like a fold, but they only have one side going down or up. So they're large step-like folds and otherwise horizontal strata. So this can happen when you have a big block of rock that gets either pushed up or sinks down. Usually it gets pushed up. And the more ductile sedimentary strata on top bends. And so it's like a sheet over a stair step. And so you have sort of a smooth overlying step. So in a monocline, you start horizontal, you dip, you bend down, and then you go horizontal again. And so this is an example of the East Kaibab monocline in Arizona. You can see the monocline going down and then leveling off again. And this large area has been eroded away, cutting into it. And so underlying this, there's a sort of stair-stepping fault in the basement rock. So here is a short video about that monocline in Arizona on the Colorado Plateau.
Today we are flying in central Utah to examine the characteristics of monoclines, which are large-scale, step-like folds in otherwise flat-lying sedimentary rocks. After watching this video, you should be able to describe and identify folds associated with regional uplift. As we drive toward the San Rafael Swell, what is the orientation of the layers of sedimentary rock you see on the highlighted cliffs in front of us? Horizontal or vertical? The sedimentary rocks in the foreground are horizontal. As we get closer to the swell, the rocks on the right are still horizontal. Look to the rocks to the left of the road. Are these sedimentary rock layers oriented horizontally? Let's take to the sky to get a better view. Now we are looking north along the flank of the San Rafael Swell monocline. While we look at it, let's discuss how a monocline forms. During the Laramide orogeny, between approximately 45 and 70 million years ago, the continental crust of western North America was compressed as the buoyant Farallon plate shallowly subducted beneath the North American plate. In response to the compression, metamorphic and igneous rocks located deep below the sedimentary rocks in central Utah were squeezed, and as a result were uplifted along high-angle reverse faults. As blocks of basement rock were displaced upward, the overlying sedimentary layers, which were originally deposited horizontally, were folded to produce a monocline. Since the Laramide orogeny, erosion has removed several kilometers of rock, exposing the interior of the monocline. A monocline is a large step-like fold in otherwise horizontal sedimentary rocks. Let's look along this part of the monocline. As you can see, these are large regional features and we are only seeing one small part. Take a look at the highlighted part of the monocline. Which part of the monocline are we looking at according to the diagram? A, B, or C? B is the correct answer. Notice how the beds on this part of the fold are inclined or tilted compared to A and C. The horizontal rocks shown on the right of this view correspond to C in the diagram. Let's travel to southern Utah to observe monoclines from different angles. Comb Ridge monocline is the linear feature shown in the middle, while the Rapley monocline is located to the left. Let's check out Comb Ridge first. The Comb Ridge monocline is quite a large feature, extending for approximately 80 miles from north to south. Now we are on the crest of Comb Ridge, looking north along the axis of the monocline. Like the San Rafael Swell, this region was uplifted and folded during the Laramide orogeny. The sandstones exposed along this ridge are tilted down to the east. Think about what we saw at the San Rafael Swell. What do you think the rocks look like to the east of this ridge, where we are no longer along the axis of the fold? You can see the top of Comb Ridge on the left, with sedimentary rock layers becoming more horizontal as you look to the right. That's because here we are further from the zone of uplift. Let's now fly over to the Rapley monocline. Let's take a look at a monocline from a different perspective, this time looking perpendicular to the axis of the monocline. Like the previous two examples, the Rapley monocline was uplifted during the laramide orogeny. However, the zone of deformation was significantly smaller, and thus more components of the monocline can be observed at one point. Sedimentary rocks along the river are flat-lying, as are those on the horizon. Along the mountain front, steeply tilted sedimentary beds are exposed in several canyons. To review, monoclines are large regional step-like folds in otherwise horizontal sedimentary rocks. Could extensional or strike-slip movement create these features? How would you tell the difference between monoclines and other folds, like anticlines or synclines?
So those were the ways that the rock can fold. Let's talk about what happens when the rock breaks instead. This is where we get joints or faults. Joints are fractures in rocks. They're just cracks. Faults are fractures in rocks, just like joints, but they're ones where the two sides have moved relative to each other. So you get a joint where something breaks, but it's just broken. It doesn't, neither side has moved. A fault is when something breaks and then it moves. And sudden movements along faults are the cause of most earthquakes. So if you have a big long fault, like the San Andreas Fault between the Pacific Plate and the North American Plate, the rocks are being, they're confined, so there's a lot of friction. And when enough stress builds up, the friction gets overcome and energy is released in an earthquake. So faults are just fractures or cracks where slip has occurred. And this allows the larger scale structure of the rock, its shape, to change because stuff is slid around. So here you can see an example of a fault. The left side has gone up, the right side has gone down, and you can see this offset layer that makes it very clear about what's happening. So let's watch a little bit about faults and the difference between faults and joints.
Today we visit a few locations in the western U.S. to investigate faults and joints. When rocks are subjected to stress, they deform by either bending, called ductile deformation, or by breaking, called brittle deformation. Ductile deformation usually occurs when rocks that are deeply buried are subjected to differential stresses, whereas brittle deformation usually occurs in the shallow crust. In this video, we focus on what happens to rocks when they undergo brittle deformation and break. After watching this video, you should be able to define faults and joints and identify their differences in the field. It is important to know that faults and joints can occur in any rock type, sedimentary, igneous, or metamorphic. For example, these fractures are actually formed by cooling of an igneous rock. For the rest of this video, we will use laterally continuous beds of sedimentary rocks to identify the sometimes subtle differences between faults and joints. A joint is a fracture in the rock in which very little or no displacement has occurred. Joints essentially appear as visible cracks in rocks. At this location, an easy way to recognize joints is to first identify sedimentary rock layers. If the layers are laterally continuous and you can easily trace a layer across the fracture, then it is a joint. A fault is also a fracture in a rock, but movement has occurred on either side of the fracture. In this outcrop, you can see the rock layers on either side have been offset and displaced. Similar to the previous outcrop, try to trace the rock layers across the fracture. If there has been movement of one side with respect to the other, then the fracture is actually a fault. Let's practice on an outcrop, shall we? Can you see the sedimentary layers in this outcrop? As a hint, a darker layer is highlighted. Now trace this layer across the outcrop. Is it continuous? Or has it been displaced? The dark layer has been displaced across several small faults. Check out this outcrop. Can you recognize sedimentary layers? How about the fractures that cut across these layers? Are these cracks in the rocks faults or joints? These are joints. Notice that the sedimentary layers have not been significantly displaced on either side of the fracture. Good work! Now that you've been introduced to the differences between faults and joints, you'll be able to practice identifying them in the field.
So in general, a fault is a fracture in the rock where there's been visible movement of the two sides relative to each other. And different forms of stress form different kinds of faults. If the stresses that form faults are compressional, you can get the crust shorten, and you can also get uplifts, causing things to move upwards. You can also get tensional stresses that form faults. This causes the crust to lengthen. When describing a fault, we describe various parts of the fault based on terminology that comes from mining. Because lots of good ore deposits are along faults. Because material gets deposited from water and other things that flow through these cracks and deposit in various places, and that often makes ore veins. So a fault plane is the approximately planar surface along which the actual movement took place. It's the plane of the crack. And then there is the hanging wall, which is the fault block on the uppermost side of an inclined fault plane. It's called the hanging wall because that's where you can hang your lamp. It's above your head. It's where you hang things. The footwall is the fault block on the lowermost side of an inclined fault plane. That's the footwall because that's where your feet go. It's where you walk. If you're, cutting a mine through this. And the fault block that has been moved up relative to the other side is termed the upthrown side. Let me. Nope. I'll have to get rid of it somehow. Dip slip faults occur when movement is parallel to the inclination. This means stuff is moving up or down. The slip causes one side to dip. The hanging wall is the rock surface above the fault, where you would hang things. The footwall is the rock surface below the fault. And the vertical displacement along this fault produces long, low cliffs that are called fault scarps. So one side of the fault moves up, and that creates these long, low cliffs that are called scarps. So this is the hanging wall block. This is the footwall block. You can see in a mine, the hanging wall block is where you would hang your lights, and the footwall block is what you're standing on. And the type of fault for a dip slip fault is determined by whether the hanging wall fault goes up or down.
Faults. A fault develops where a rock structure is broken and forcibly displaced. The movement along a fault may be vertical, horizontal, or a combination of both. A normal fault develops from tensional stress, the stress that results when a landscape is rifting or pulling apart. Movement along a normal fault is predominantly vertical, although the orientation of the fault plane may not be perpendicular to the surface. As the landscape is extended, notice that one side of the fault plane drops down relative to the other. The fault scarp formed along the uplifted mountain front eventually erodes away, leaving little surface evidence of the fault. Many landforms can develop from normal faulting, including tilted fault block mountains, downdropped basins known as grabens, and uplifted mountain blocks called horsts. A reverse fault develops from compressional stress. Movement along a reverse fault is also predominantly vertical, although in a type of reverse fault known as an overthrust fault, the upthrown block overrides the downthrown block at a very low angle. As the landscape is compressed, one side of the fault is pushed up over the other side. Once faulting ends, erosion gradually wears down the uplifted mountain. A strike-slip fault develops from shear stresses, causing one side of the fault to move horizontally past the other. Notice that horizontal movement along the strike-slip fault may displace the course of a stream. Such offset streams commonly develop from ongoing displacement along a strike-slip fault.
So, the three types of faults. A normal fault is when the hanging wall moves down with respect to the footwall. This is caused by tensional forces, things pulling apart. A reverse fault is the opposite. That's when the footwall moves down with respect to the hanging wall, or the hanging wall moves up with respect to the footwall. This is caused by compressive forces. And a strike slip or transform fault is caused by shear forces where the stresses are parallel to the fault plane. This is, horizontal motion. So normal and reverse faults are vertical motion, strike slip or transform faults are horizontal motion. So dip slip faults, that covers both normal and reverse faults, occur when movement is parallel to the inclination. The hanging wall is the rock surface above the fault, the footwall is the rock surface below the fault, and the vertical displacement will produce low cliffs called fault scarps. So for dip slip faults, you have normal, reverse, and if you have a reverse that's at a very shallow angle, it's called a thrust or overthrust fault. So we'll start with talking about a normal fault. You have tensional stress, pulling things apart in order to lengthen the crust. The hanging wall block will slide down, causing things to spread apart. And then the upper portion of the footwall block will erode away. In a reverse fault, the opposite happens. The footwall block gets pushed above the hanging wall. The hanging wall block gets pushed above the footwall block, and the hanging wall block is what erodes away. So here's
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to name the 5 major kinds of faults and describe the relative motion of the blocks of rock on either side of those faults. So faults, just to review, are breaks in the Earth's crust along which there has been movement of one side relative to the other. If there hasn't been any movement, we call it a joint. But with faults, we see the offset of some marker bed. We describe faults with terminology that was developed by miners. Often faults are sites of mineralization. In other words, there's important ore minerals that form along the fault surface. And so as miners went in there to extract those ores, they described the block of rock above their head as the hanging wall block, and the block of rock below their feet as the footwall block. We can describe many different faults in terms of the relative motion between the hanging wall and the footwall blocks. Let's start with a normal fault. A normal fault is where the hanging wall block moves down relative to the footwall block. So this is what you would expect in an area of tectonic tension. So that stress acting on the rock breaks it, and blocks of rock slide down the face of their neighbors. On the other hand, if the tectonic situation is one of compression, then the stresses are going to break that rock along a reverse fault. In a reverse fault, the hanging wall block moves up relative to the footwall block. It's the reverse of normal. There's a variation on a reverse fault called a thrust fault. And basically what's going on with a thrust fault is that the angle of the fault is relatively low. In other words, it's a pretty shallowly dipping fault. And sometimes these thrust faults are actually almost horizontal. An example of a thrust fault is seen in Glacier National Park, Montana, in the United States. Here, a thrust fault formed, and it brought Precambrian age rocks on top of Cretaceous age rocks. Then erosion went to work on the landscape, and it actually cut through the fault surface, leaving behind a little isolated remnant of the hanging wall block, which is called Chief Mountain. So Chief Mountain, if you look at it here, actually has the Lewis thrust fault running along its base, and you've got Cretaceous age rocks below that thrust fault, and you've got Precambrian age rocks above it. So older on top of younger, the opposite of what superposition would predict. There's another kind of fault where the fault surface is more or less vertical. So we're tracing out the fault surface right here on the surface, and you can see that there is an offset of these light-colored layers towards the right on the opposite side of the fault. So this is what we call a strike-slip fault. All the motion is in the strike direction of the fault trace. An example of a strike-slip fault is the Alpine Fault in New Zealand, which is a right lateral strike-slip fault, or the San Andreas Fault in California. There's one more kind of fault that we need to mention, and that's called an oblique slip fault. The motion on an oblique slip fault is neither in the strike direction nor in the dip direction, but if we consider some point that was connected before faulting, and we draw a line from the previous position to the post-faulting position, we can see that that line is inclined at an angle. It's neither parallel to the strike of the fault nor parallel to the dip. Instead, it is oblique to both. So it has elements of strike-slip motion and elements of dip-slip motion. What we would end up seeing on this fault surface.
Sorry that it caught out there. You can see these marks or striations. I don't know what's up with the video there. I think that might have just been cut off in the original video source. So for dip slip faults, normal faults are characterized by the hanging wall moving down relative to the footwall. They're associated with tensional stress as the rocks pull apart. Larger scale normal faults get associated with fault block mountains. So for example, the Basin and Range Province, these uplifted blocks are called horsts, and the downward blocks are called gravens. So fault block mountains are formed by dip slip faults. You also get half gravens, which are tilted fault blocks, and detachment faults represent the boundary between ductile and brittle rock units, where one portion bent, the other portion broke. So here we have a graben and a horse, where things sort of tilted, and we have breaking above this detachment fault and bending below it. So here are some examples of normal faulting in the Basin and Range Province. And here's some.
Hello, I'm Michael Collier. Standing on the floor of California's Death Valley is a lot like riding in an elevator whose cables have just been cut. In geologic terms, the valley is sinking that fast. Where's the evidence? Well, did your ears just pop? Maybe ear popping isn't enough to convince you, though. Geology, like all sciences, has got to be evidence-based, so let's dig a little deeper for proof that the valley is sinking. We'll be looking from up here in the air and from down below on the ground.
On this field trip, we'll see that geologically, Death Valley is an active landscape. We'll follow as rocks that were once flat and horizontal are folded like chewing gum and tipped up at crazy angles. And we'll see that different types of faults are pulling Death Valley apart in front of our eyes. For starters, Telescope Peak, the highest point in Death Valley's Panamint Range, stands more than 11,000 feet above sea level. Last time we checked, Badwater, just 15 miles away, lay 282 feet below sea level. Topographic differences like this would be hard to imagine in a more stable geologic setting. Artist Drive is just up the road from Badwater, where a fault is visible. Vertical movement sent these mountains up, and the valley down. The bright line is a scarp. It's the trace of a type of fracture called a normal fault, where rocks slide down the fault surface. What do you think? Does normal faulting happen when a landscape is under tension or compression? Tension. Movement here happened so recently that erosion has yet to erase the fault scarp. What comes to mind when you see an unexpected line across a landscape? Maybe it's a fault, or it might be the tilted edge of a sedimentary layer. Of course, that line could be the preserved, wave-cut shoreline of an old lake. Or it might just be the road. Death Valley does keep you on your toes. As soon as ranges began to rise above Death Valley, they started shedding prodigious amounts of sediment. The material piled up in steep alluvial fans that spread from the foot of the mountains out onto the valley floor. Rain falls infrequently here, so the fans are built in fits and starts as passing storms locally dump their deluges. Here in Echo Canyon, this breccia is composed of angular pieces of rock that didn't roll down some lazy river and become rounded. With such steep mountains, debris flows triggered by storms can carry a lot of rock. Together, these alluvial fans and debris flows are further evidence that Death Valley exists within a tectonically active region. There's still more evidence of motion at Death Valley. Rock layers can be tilted when they're caught up in mountain uplift. These Paleozoic strata were flat when deposited 300 or 400 million years ago, but now they sit at a precarious angle on the flank of the Panamint Range near Johnson Canyon. During the early Mesozoic, maybe 200 million years ago, this landscape was being squeezed, and its rocks were being folded. Sometimes the layers were compressed so much that they tore along thrust faults where rocks are pushed up along the fault surface. But times have changed, and today the area is being pulled apart. Can you suggest a reason for this reversal of forces? Death Valley is now part of the Basin and Range Province, a region centered in Nevada that spills into the neighboring western states. The province is packed with mountain ranges all aligned roughly north-south, each separated by intervening basins. The region is caught in the middle of a colossal tug-of-war inspired by relative motion of the North American and Pacific plates. Near Death Valley, the basin and range has stretched like taffy 150 miles east to west in the last few million years. This stretching occurred along faults. They can have different geometric orientations, but they all add up to extension within the basin and range. Rocks on either side of the Furnace Creek Fault have been offset 30 miles over the past 10 or 12 million years. The Furnace Creek is an example of a strike-slip fault where rocks slide sideways past each other. Once you've clearly seen a fault like this, it's hard not to believe that rocks really do move. The Furnace Creek Fault lies to the north of and roughly parallel to its counterpart, the southern Death Valley Fault Zone. Both are strike-slip faults that accommodate some of the Pacific and North American plates' motion. 690,000 years ago, magma rose to the surface along the southern Death Valley Fault to form a cinder cone. Since then, the fault has continued to slip in its right lateral fashion, cleanly ripping the cone in two. Sometimes geologic evidence is so compelling, so overwhelming, that you're left breathless when you finally understand what the rocks are trying to say. It can make your ears pop. Take the turtleback at Copper Canyon, for example. This is the exposed lower surface of a low-angle fault on the east side of Death Valley. An entire mountain range slid off the back of the Black Mountains along this turtleback. Skidding rocks polished the turtleback on their way downhill, creating this grooved surface called a slickenside. Go ahead, run your fingers up and down it. You can feel the direction of movement. Geology is full of big ideas, but you won't find many other places where the ideas are so tangible. Death Valley is a terrain that is being torn apart, extended as its mountains rise and valleys fall. Its rocks lay unobscured on the surface, willing to tell stories. All you have to do is look and listen. Death Valley is being pulled apart by tensional forces, squeezed together by compressional forces. Death Valley is being pulled apart by tensional forces. We've been looking at evidence that Death Valley has been under tension and is being stretched apart. Do these views suggest tension or compression? Sheep Mountain in Wyoming was compressed. This set of normal faults near Arches National Park in Utah was created by tension.
So we talked about normal faults. Reverse faults are characterized by the hanging wall moving up relative to the footwall. They're associated with compression. And thrust faults are really shallow reverse faults with angles less than 45 degrees. So the overlying plate moves almost horizontally. The big deal with thrust faults is you can get older rock ending up on top of newer rock. They're most pronounced along convergent plate boundaries. You get these megathrust faults where one plate is subducting under another. But we also get big thrust faults in places where two continental crust regions impact and pile up mountains. So some examples are the Alps, the Northern Rockies, the Himalayas, and the Appalachians. All have lots of thrust faults because they were compressed and both folded and piled up by thrust faulting. So reverse faults, the hanging wall block goes on top of the footwall block. The crust gets shorter and taller. So here's a reverse fault.
A reverse fault is a type of dip-slip fault in which the hanging wall block moves up relative to the footwall block under compressional stress.
So that's the reverse fault. That shows what's actually happening. And then a thrust fault is a very shallow reverse fault where you can get older material on top of younger material. So this is the thrust fault. So it's similar to, it's a type of reverse fault, but it's a very shallow one.
A thrust fault is a low-angle reverse fault. As you can see, thrust faults can result in older layers being thrust over younger strata.
Now, strike slip faults are places where instead of the movement being down, up or down along the dip direction, they're along the strike direction, side to side. So they're characterized by placement that's horizontal and parallel to the strike of the fault. So types of strike slip faults, well, the side you're looking at can be moving to the left or the right. That's how you characterize them. Right lateral, if you're looking at the opposite side of the fault, the opposite side moves to the right. That's a right lateral fault. And the left lateral, if you're looking to the opposite side moves to the left. That's all the difference. And it'll be the same on both sides of the fault. So if I was on if there was a right lateral fault between us and it slipped, I would move this way. If it was left lateral, I would move this way from your point of view. So large strike slip faults that come through the crust to accommodate plate motion are called transform faults. These are the big famous ones. For example, California's San Andreas fault. But there are also small strike slip faults as well. So some of the interesting things that can happen with strike slip faults is you can get what's called offset drainage and weird funny things going on where if you have a stream that was crossing the fault and the two sides move, the stream can get offset. You get a linear valley along that slipping zone of the fault. And you can get areas that are like sunken in and flood and form side ponds. So this is a strike slip fault. You can see how things get offset. So here's sort of all the faults together. For a fault, you have a footwall side, which is below the fault plane, the hanging wall side, which is above the fault plane. If the hanging wall moves down, it's a normal fault. If the hanging wall moves up, it's a reverse fault. If the hanging wall moves up at a very shallow angle, it's a thrust fault. If the hanging wall doesn't move up or down, but moves to the side, it's a transform or strike slip fault. And here is a summary of all the different ways that faulting and folding can occur.
Hello everyone, this is Earth Science teacher Tim Martin, and in this video I want to introduce you to the geologic concepts of folding and faulting. When we look for faults and folds in the Earth, what we're really doing is looking for past evidence of plate tectonic motion. Let's take a minute to review the basic motions of plate tectonics. The first of the three motions is divergent motion. This occurs when magma comes up from deep within the Earth. This typically happens in the middle of the ocean. It generates earthquakes as the plates move apart from each other. This may also happen on continental plates as well. The next type of motion, convergent motion, happens when plates collide. Here we can see an oceanic plate subducting beneath a continental plate. As the plate subducts, it cracks and breaks, generating earthquakes. Finally, we have transform motion. This occurs where two plates slide or grind past each other. Again, this generates earthquakes. Now let's take a look at the structures identified with each of these three types of motion. To start off with, let's talk about rifts or cracks. When the Earth is pulling apart or forces are acting on it in opposite directions, the crust will thin, stretch, and possibly crack. These cracks are often known as rifts. This is caused by tension or divergent motion. A normal fault also happens with tension or divergent motion. If the rock is more rigid and less likely to stretch, it may simply crack, and when it does, one block may drop lower than the other. This is what's called a normal fault. Opposite the normal fault, we have a thrust or reverse fault. This occurs from compression or convergent motion. When two plates are pushing against each other, one plate may go down or another one may go up. This creates a thrust or reverse fault. Finally, a transform fault or a strike-slip fault occurs with lateral stress. When two parts of the Earth's surface are moving in opposite direction with respect to each other, one may slide, causing a transform or a strike-slip offset. While sometimes rocks break with faults, sometimes they're soft enough to fold. A fold occurs with compression or convergent motion. Sometimes rock layers may fold with an upward bend, other times they may form with a downward bend. Both types of folds occur with compression or convergent motion. An upfold is referred to as an anticline. The downward or U-shaped fold is referred to as a syncline. Let's take a look at what this looks like with real geology. Can you identify the motion from these real images? Let's take a look at these 5 different features. Thingvellir National Park in Iceland is one of the classic locations where the Earth is splitting apart. On the right-hand side of the picture, we see the North American plate. On the left side, the European plate. As the plates are splitting apart, this rift or gap is opening up. This occurred through divergent motion. This picture of the Hayward Fault was taken in Fremont, California, in Central Park. You can see when the road planners built this road, they didn't intentionally offset the sidewalk and curbing. What happened here is part of the road was built on the North American plate, and the other part of the road was built on the Pacific plate. Here's the fault line, and we can see the further section is moving northward, where the side that the photographer is standing on is moving towards the south. Moab Fault is a dramatic fault that was revealed in a road cut just outside of Arches National Park in Utah. Here we can see several very large faults. As we identify the previously aligned layers, we can see that this brown stripe used to all be the same layer, but now has been offset with several normal faults. This represents divergent motion or tension. Browns Canyon of the Arkansas River goes through Salida, Colorado. Here we can see rock layers that have been folded. This must have occurred through compression or convergent motion. It's impossible to make a fold by pulling. Going from a large scale to a rather small scale, in Mosaic Canyon in Death Valley National Park, California, we can see this small layer was offset. The fault indicated in red, and these yellow layers are offset with a little bit of overlap. This indicates that this was a reverse fault caused from compression or convergent motion. So let's take a little quiz. Can you identify the motion in these next 5 images? Feel free to pause the video between each image. Number 1 is Katobe Knob, located in the Cedar Mountain Recreation Area in the San Rafael Swell in Utah. Number 2 is a rock structure that I found at Noosa Heads in Queensland, Australia. Number 3, a road cut near Orderville, Utah. Number 4, rock layers west of Wild Rose Campground on Wild Rose Road in Death Valley National Park. Number 5 is specifically called Earthquake Fault, located just outside Mammoth Mountain Ski Area in Mammoth Lakes, California. So, could you identify all 5 of these images? What sort of plate motion caused each? Are they normal faults, reverse faults, folds, or rifts? Let's take a look at each. Number 1, Katobe Knob in the San Rafael Swell in Utah. First, we identify the fault plane, located here. Then we identify the layers that used to line up, here and here. So we can see, because of the overlap, this must have formed from compression or convergent motion. Number 2, Noosa Heads in Australia. Again, the first thing to do is identify the fault plane, located here. Then the layers that as they used to match up, here and here. Because of the lateral offset, we understand this must have been transform or a strike-slip fault. Number 3, again, this is a road cut in Orderville, Utah. Let's identify the fault plane, leaning from left to right across the image. See the double brown lines towards the bottom of the image? These used to match up with each other. Thus, this is a normal fault, formed through tension or divergent motion. Number 4, along Wild Rose Road in Death Valley National Park. We can obviously see folds. These folds must have formed from compression or convergent motion. Finally, number 5, the earthquake fault near Mammoth Lakes, California. Again, this is a great example of a rift where the earth was experiencing tension and cracked open, causing this split in the rocks. Would you like a little more practice identifying folds and faults? You can download a slideshow of images that I've taken from around the world of places where we can see convergent, divergent, and transform plate motion. Thanks for watching, and I hope to see you again on another Team Art Science video.
Mostly joints are fractures in the rock, but there's no rock movement, and most joints appear in parallel groups, like you can see here. So often joints are a whole bunch of parallel lines, cracks in the rock. And that is where we're going to stop for today. So I will see you all next week on Tuesday. We will have the test on Thursday. Yeah, and we will continue on from there. Let me.